Hello friends, I am Dr. Nitisha Shrivastava from Indraprastha Engineering College. Welcome back to the control system lectures. This lecture is part 2 of the time response of prototype second order system. In the part 1 lecture, we had derived the relation of C of t of prototype second order system when subjected to step input. We had seen that the characteristic equation we have seen that the time response C of t is obtained, and then we found out the roots of the characteristic equation S1 and S2. Now, we will see that what is the role of the damping ratio, damping factor, and how it affects the stability of the system. So, stability of the system means that what is the location of the roots on the S plane. So, we will understand that how the damping ratio affects the location of the roots and in turn affects the stability of the system. So, we are going to understand the physical significance of zeta omega n. We are going to understand the physical significance of zeta omega n and the damping ratio zeta. So, this is the time response equation as obtained from part 1 lecture of the time domain response of prototype second order system. C of t is 1 minus e raised to minus zeta omega n t. So, exponential term has minus zeta omega n multiplied by t upon 1 minus zeta square sine of this quantity, that is omega n root of 1 minus zeta square plus tan inverse 1 minus zeta square upon zeta. This is the equation as obtained from a time response equation. Now, we can see that we have used the term zeta omega n. Why? Because the exponential term of the time response is having a constant value minus zeta omega n. So, minus zeta omega n is a constant that is multiplied to t in the exponential term. So, what does this signify? What is the meaning of this term? It means that zeta omega n controls the rate of rise or decay of the unit step response. So, that is why we are terming this zeta omega n as damping constant. Why? Because it is a value which is multiplied to the exponential term t of the exponential term, and therefore, it is responsible for the damping of the system. It controls the decay or rise of the response of the unit step response, and therefore, zeta omega n controls the damping of the system. This means that it controls the damping of the system, and therefore, zeta omega n is known as the damping constant or the damping factor. And since zeta omega n is a constant which is multiplied, so inverse of zeta omega n is the time constant of the system. So, we have understood that what is zeta omega n, what is the role of zeta omega n. So, that value is basically responsible for the damping of the system. It indicates us the rate and rise or the rate of rise or decay of the unit step response. Now, here we will look into the value of zeta as equal to 1. This S1 and S2 are the roots of the characteristic equation of a closed loop prototype second order system. Minus zeta omega n the real part plus or minus j omega n root of 1 minus zeta square is the imaginary part. Now, here we can see that when you put zeta equal to 1, as we have already defined, zeta omega n as the damping constant. And now we are using this zeta as 1. So, when you substitute zeta as 1, so what happens to the root? Root of the equation becomes simply minus omega n. Here we are substituting zeta as 1 and here we are substituting the value of zeta as 1. So, what happens to the root of the characteristic equation? It just becomes minus omega n. There are two roots and the two roots are having equal value, that is minus omega n. So, as mentioned, the two roots of the characteristic equation are real, there is no imaginary term, they are real roots and they are all both equal. So, what does this term signify? That we do not have this j quantity here, that is the imaginary part is 0. Imaginary part is 0 clearly indicates that there is no oscillation. There are no oscillations in the response and the system is critically damped. Now, what is the meaning of no oscillations? Now, here if this is our time t and this is c of t. So, and this is the step input, as we are talking about the time response when subjected to a unit step input. So, we have only the real roots, that is the response of the system is moving to the final value without having any oscillations. So, there are no oscillations and since there are no oscillations, the system is directly, the response of the system is directly shooting to the steady state value and therefore, the condition when zeta value is equal to 1 is termed as the critical damping case, because zeta omega n, as we have already seen, it is a damping constant and when zeta is equal to 1, here we have seen the roots are both real and equal, there are no imaginary parts and this leads to the response shooting to the value. Now, here we can see what do you mean by the roots are real and equal. That means they both lie on the left half of the S plane. The roots lie on the left half of the S plane, right. So, zeta omega n is known, zeta is equal to 1 is known as the critical damping and as we have mentioned zeta omega n is a damping constant. So, when zeta value is 1, so when zeta value is 1, what is the damping constant of a critically damped situation? In this case, the damping factor is simply omega n. Now, what is the role of zeta? Here zeta is 1 and when zeta is 1, the time constant, the damping constant is equal to omega n. So, what we are writing this here? Zeta omega n upon omega n is nothing but zeta. So, this is termed as the damping ratio. Zeta is equal to zeta omega n upon omega n, which is equal to actual damping factor upon damping factor at critical damping. So, here we can see that zeta is nothing but zeta omega n upon omega n. This is actual damping factor upon damping factor at critical damping. Therefore, the condition zeta is equal to 1 is known as the case of critical damping. We can also work out this relation with respect to the response of the system. We have seen that C of S is equal to this. Now, how is this relation obtained? We know that the output response of a closed loop or the closed loop transfer function is given by omega n square upon 2 2 zeta omega n s plus s square. It's written here, the terms are interchanged here. Here if you substitute the value of zeta as 1. Now, when zeta is equal to 1, we get that r of s is 1 by s. So, omega n square s square plus 2 omega n s plus omega n square. So, what is the characteristic equation of a second order system when zeta is equal to 1? It is this characteristic equation, delta s becomes s square plus 2 omega n s plus omega n square. And what are the roots here? S plus omega n the whole square. So, now we are applying the partial fraction expansion to this. 1 upon s is equal to 1 upon s into omega n square, and the denominator having 2 roots, as we have already seen, it is minus omega n. Applying partial fraction expansion, it is a by s plus b upon s plus omega n plus c upon s plus omega n the whole square. The value of a is 1, and after solving this partial fraction expansion, we obtain the value of a, b and c. A is 1, b is minus 1 and c is obtained as minus omega n. Substituting the value of a, b and c, this is what we obtain. So, in this is the condition, or this is the response of the S domain response of the system when zeta is equal to 1. Zeta is equal to 1 is the case of critical damping. We are applying inverse Laplace because we want the value of C of t. C of t is this, C of t inverse of 1 by s is 1 and e raised to minus omega n t. We can see that there is no term zeta since it is equal to 1, and minus omega n t e raised to minus omega n t. Just rearranging the terms, the output response C of t is 1 minus 1 plus omega n t into e raised to minus omega n t. So, looking into this equation, as we have mentioned here, there are no oscillations. So, we can see that there is no sine term here, and therefore, the response of the system will be of this kind, right. So, C of t is this when the case is of critical damping, that is zeta is equal to 1. So, what we can infer here? There is no sinusoidal term and the oscillations just disappear when zeta is equal to 1. So, that is why it is known as the case of critical damping. And what about the time constant? Damping constant zeta omega n, and zeta is equal to 1. Therefore, damping constant is omega n simply, and the time constant is 1 upon omega n. So, this is the case we have discussed for the value of zeta which is equal to 1. Now, here we will use the other case, that is the damping is 0, zeta is equal to 0 means the system is having 0 damping, the value of damping is 0. The parameter omega n is defined as the natural undamped frequency. We will look into why it is known as natural undamped frequency. What happens when zeta is equal to 0? We have derived this, that the roots of the characteristic equation are S1 and S2, and the values of S1 and S2 as known is minus zeta omega n plus or minus j omega n root of 1 minus zeta square. when you are substituting zeta is equal to 0. When zeta is equal to 0, we do not have any real term, that is the roots are not having any real term, and we are left with only imaginary term, that is plus or minus. When the case is zeta is equal to 0, the roots are simply plus or minus j omega n. What does this mean? This means that there is no real term in the roots. There is no real term in the roots. That means the roots are lying on the imaginary axis. So, the roots are lying on the imaginary axis for the case when there is no damping, and the roots of the characteristic equation are purely imaginary. So, we have seen that we just rewritten the equation. We have just rewritten this equation of C of t. C of t is equal to 1 minus e raised to minus zeta omega n. So, wherever we have zeta, we are just putting it equal to 0, because we are talking about the case of 0 damping, where zeta is simply equal to 0. Now, here when C of t, what will be the C of t? When zeta is equal to 1, C of t will be 1 minus sine omega n t plus 90 degree. Now, what does this signify? So, there is here we having a sine term, and the complete response is a cosine wave of frequency omega n. The roots are lying on the imaginary axis. This means that the response is having only pure oscillations, and there is no real term. So, and there is no exponential term here, there is no real term, we have only the sine term. So, that means the output is a cosine wave of frequency omega n. So, what will the response look like? The response will look like something like this. There is sustained oscillations. If this is our time axis, this is time and this is C of t. Therefore, omega n corresponds to the frequency of the undamped sinusoidal response. So, this means that the output of the system will have only oscillations which do not damp out. And what is the frequency of those oscillations? The frequency of those oscillations is omega n, and here we have mentioned that we are going to tell why omega n is termed as an undamped natural frequency. It is termed as undamped natural frequency because the oscillations of the output do not damp out. So, this is the condition known as sustained oscillation. So, when there is no damping for the system, the output response simply indicates that there are sustained oscillations, because the roots of the characteristic equation lie on the imaginary axis. The two roots obtained lie on the imaginary axis, the conjugate pair here. Now, we will see the next case of underdamped. Here the value of zeta is neither 0 neither 1, it is lying in the range between 0 and 1. So, the case of zeta equal to 1 is the case of critical damping, and the case of zeta equal to 0 is about the output having sustained oscillations, and that is the 0 damping case. So, here as rewritten, the two roots of the equation are S1 and S2 minus zeta omega n plus or minus root of 1 minus zeta square multiplied by omega n. Now, we are now interested to know what would be the magnitude of this roots. We have a real term as well as the imaginary term. So, how do we find the magnitude? It is simple, x square plus the real square plus the imaginary square in the under root. So, that is what we have done here. We have used this minus zeta omega n square plus this, and when you solve for the magnitude, we get the magnitude as omega n. So, when zeta is lying between 0 and 1, what is the magnitude of the roots? It is omega n that we have shown here. I have shown here. Here it is, basically we are terming this as a real part, that is alpha, and this is the imaginary part which is known as omega d. So, it is alpha plus minus j omega d. Okay. So, we are having two roots, that is the on the left half of the S plane. So, the system is stable, and omega n, this is the distance of the real part, and this is the distance of the imaginary part, and omega n is nothing but the radial distance from the roots to the origin of the S plane, and omega d is the imaginary part of the root as mentioned, alpha is the real part of the root, and looking here, this is theta. So, zeta is nothing but we can see it is cos theta, because alpha is zeta omega n and this is simple omega n. So, what is cos theta? Cos theta is zeta omega n upon omega n. So, cos theta is simply zeta. As mentioned here, zeta is the cosine of the angle between the radial line to the roots of the negative roots and the negative axis when the roots are in the left half of the S plane. So, it is zeta is equal to cos theta. So, what we are inferring from this? It is a S plane, real part, imaginary part, and this is the distance we have drawn as the radial distance. Now, since zeta is not equal to 0, so this is the condition where zeta is not equal to 0, because when zeta is equal to 0, we have sustained oscillations. Now, this is the pure case of zeta not equal to 0, and the response C of t is therefore not a periodic function, and omega d here is not a frequency. There are two quantities in the real and the imaginary part, omega d on the imaginary part. So, therefore, this for the purpose of reference, omega d is sometimes defined as the damped frequency. So, what will the relation look like? Let's solve here. So, the typical response will look like this. If this is our unit step input 1, so response will simply look like this. So, there are oscillations, but the oscillation die out after a certain period of time, and therefore, we define it as damped frequency, omega d as the damped frequency. The oscillations are not sustained, they damp out after a certain period of time, and therefore, omega d is also referred as the frequency of the damped oscillations. So, these oscillations damp out while reaching the steady state value. So, a brief summary of the location of the roots of the characteristic equation. Now, we can see here we have studied the case of zeta lying between 0 and 1. So, here the roots are minus zeta omega n plus or minus j omega n root of 1 minus zeta square. So, here zeta omega n, that is the real part, is on the left half of the S plane. So, it is less than 0, it is the roots are on the negative real axis, and therefore, the system is stable, and this is the case of under damped condition. When zeta is equal to 1, that is the case of critical damping. As we have seen, there are two roots and the roots are real and equal. So, that is the case of critically damped condition. Here there are no oscillations, and as we have seen, the response reaches the value, steady state value, without any oscillations, and zeta is equal to 0 is a pure case of 0 oscillations, 0 damping, that is having sustained oscillations, and therefore, it is known as the case of undamped condition. Zeta is equal to 0 is 0 damping, and it is known as the undamped condition. Now, what happens when zeta is greater than 1? As we know that the roots of the equation are minus zeta omega n plus or minus j omega n root of zeta square minus 1. Now, this is the case when zeta is greater than 1. When zeta is greater than 1, what happens to this condition? Now, here we can see that when zeta is greater than 1, we have a minus 1 root outside, and therefore, this equation now becomes, when the case is zeta greater than, we are talking about the case when zeta is greater than 1, and therefore, we are left with no imaginary term zeta omega n, here I will write it here, minus zeta omega n plus minus, we are having omega n because this term has become common, root of zeta square minus 1, because originally it is 1 minus zeta square. So, this is 1 minus zeta square, and when this is taken outside we get it as zeta square minus 1. So, this is the case of overdamped. Overdamped case means this is the case of critical damping. Overdamped means the system response reaches the final value after a very long time. So, such systems which are overdamped are known as sluggish systems. The system are very stable, and the response of the system to reach the final value takes a larger time, and therefore, it is known as sluggish systems. And this is the case of zeta less than 0. When the value of zeta is less than 0, what does we mean by that? When zeta is less than 0 means it is having a negative value. Zeta is having a negative value because its value is less than 0, and since it is having a negative value, what happens to the real part? Here real part is minus zeta omega n, but since zeta is a value which is less than 1, it is having a negative value, the real part of the root becomes positive. So, real part of the root becomes positive means that the roots are lying on the right half of the S plane. Means when the roots are on the right half of the S plane is the condition of being unstable. So, we have written here that this is the case of negatively damped condition. Negatively damped condition in the sense that the system is unstable. So, this is a brief summary of the relationship between the system dynamics with respect to the value of zeta. That is, value of zeta means the damping of the system. Damping of the system affects the location of the roots and thus the stability of the system. So, this graph typically depicts the response of a system for different values of zeta. So, here it is this is the response y axis c of t, and this is time axis omega n into t. So, we can see that zeta ranging from 0.1, 0.2, 0.3, 0.4, the overshoot value is reducing as the value of zeta from 0.1 is nearing the value of 0.8. However, in the case of zeta equal to 1, there is no oscillation, that is the case of critical damping, and we can also see that when zeta is greater than 1, that is 1.5, the system takes certain time to reach the final steady state value, and as increasing again for 2, zeta equal to 2, which is a value greater than 1. So, the system is stable, very much stable, but it takes certain time to reach the final steady state value. So, this graph typically depicts the prototype second order system unit step response for various damping ratios. So, we have understood how zeta affects the damping of the system. Now, here in this we can see that how would be the response of the system when the cases are regarding zeta equal to 1. This is the case for zeta equal to 1. Here we can say that when zeta is equal to this is zeta greater than 1, this is the condition zeta greater than 1, we can say that the response takes more time to reach the final steady state value, and when the roots are real and equal, that is the case of zeta equal to 1, and this is the case of 0 less than zeta less than 1. So, this is the response of the system for the case, and this is the response of the system. As I told you, it is having sustained oscillation. So, this is the case of zeta lying between -1 here, and this is zeta is less than -1. So, these are the typical graphs for the different values of the root locations. So, a brief summary of what we have discussed today regarding the second order control system. Here the left half of S plane corresponds to positive damping, that is the damping factor or damping ratio is positive. Positive damping causes unit step response to settle to a constant value in the steady state due to the negative exponent minus omega n t, e raised to minus omega n t. We have this term. So, as we have seen, how will the response? The response is like this. Right. So, these oscillations damp out having both positive overshoots and negative overshoots because of the term existing in the response e raised to minus zeta omega n. These oscillations die out and the system is stable for the condition of positive damping. The right half S plane corresponds to negative damping, as we have seen that the roots lie on the right half of the S plane, and negative damping gives a response that grows beyond and that is without bounds with time, and the system is unstable. And when the roots are on the imaginary axis, it is the case of zero damping. Zero damping results in sustained oscillations, and this condition is known as the system to be marginally stable or marginally unstable. So, this slide basically tells us about the summary of the location of the roots, that is location of the characteristic equation roots, which is playing an important role in the transient response of the system. So, the damping factor, the damping ratio, and the role of zeta, that is zeta equal to 0, zeta equal to 1 or zeta lying between 0 and 1 is discussed here. Thank you.